Thank you, everyone, for staying a little bit longer here today. It's a beautiful facility. I think we've made a really good choice of having it in Watford City. And please fill out your surveys when they do come to you, so we could get some feedback from everyone. So I had the opportunity to attend the Produced Water Society's annual conference in Houston, and I want to thank the Select Water for helping me obtain that. At this conference, it was very interesting and enlightening. A lot of it had to do with the technologies for recycling produced waters, and then touching on how you can use that water or the salts that are on the backside. And so a lot of this talk will sort of hinge on a little bit of the information that I learned there. And I've gathered some other information as well, and essentially made some back of the envelope calculations. Don't take them and wave them around, but you can kind of get a sense for what opportunities we have in North Dakota. So, okay, so one of the things I think that is important to sort of figure out is, where can we use recycled produced waters? And so I pulled this from New Mexico's. You learned this morning from Rick that there's some consortiums in New Mexico, Texas, Colorado, and they are focused on produced waters. And so some of them are very active. I was very impressed with both of New Mexico's and the one that's based out of Lubbock at Texas Tech. But here's an example of a survey that had been done to sort of figure out, okay, what can we use this water for? And so basically, this survey outlined many different things, and certainly reusing the water in the oil and gas industry is probably a high priority, right? And so, but there's other things we can do with that. And so I'm just going to highlight a couple of them that we're going to talk about today are the agricultural uses, and specifically irrigation for crops. And also, can we use this for livestock watering? Can we use it for reclamation? And then on the other, ending with what is in this salt that we can extract, or what is in this produced water that we can utilize? And so that'll be sort of the tone of everything. But I think it's important to sort of step back and say, before we say, all right, we're gonna recycle everything, is figure out, can we use it if we do? And so I pulled this from the Water Center at UPenn. On the top, you see extremely high risk, meaning that if your state is on the bottom, it's probably a low risk, and if it moves up towards the top, it's more of a high risk for water stress. And so if we look closely, if we just look at Texas, New Mexico, and North Dakota, well, there's a reason why there's a high need in New Mexico. They are very water stressed. And so they have gone forward with trying to figure out how can they reuse produced water, because it's already at the surface. They just have to sort of purify it a little bit. But you can see also Texas, and then you see North Dakota buried down in that low to medium category. We don't necessarily have a water stress state. Water will never not be an issue in North Dakota. Sometimes it's too much, sometimes it's too little, but in Texas and New Mexico, it's always too little, right? And so we have to kind of remember that as we move through this presentation, and as we think about produced waters, is like, what are we going to do with those waters? Okay, so you've heard this maybe before, but can we use produced waters legally? And so if you look at Code of Federal Registry, yes, you can. If you're west of the 98th meridian, the produced water has a use in agriculture or wildlife propagation. And so legally, west of the 98th, and certainly we are, federally, it's legal. And so we started looking at these other states. So this is in Texas. They have this House Bill 3516 encourage the commercial recycling of liquid oil and gas waste, including produced water. Why? Because they're water stressed, and they see this as an opportunity. And so these are the things that sort of this conference that I went to sort of talked about. And so also in New Mexico, There was a bipartisan effort to encourage and facilitate recycling and reuse of produced water by oil and gas producers for agriculture, municipal, and other uses. Okay, so yes, there is a need, and it's legal. Is it illegal in North Dakota? Yes, in general. Regardless of proposed use, all water users, except those reusing fossil byproduct water, which is what we're talking about, shall secure a water permit. So basically, yes, fossil water can be recycled and reused. Okay, so legally we can do that also in the state of North Dakota. Okay, so we're going to go through some calculations and some things: irrigation, reclamation, storage, livestock, and then the last thing we'll touch on is what's in the actual brine itself. Okay, so this report came out in 2020. It's from the EERC. You can run the Google machine. You can find it and download it. But basically, I want you to focus on the right-hand side. North Dakota could anticipate the need to manage between about 2 billion and 2.7 billion barrels per year of produced water annually. That's a lot, right? I mean, that's not trivial. And so how do you think about recycling or even reusing all of that water, right? And so for this talk, we're just going to assume that 50%, we're going to utilize 50% of that water, as opposed to thinking every drop that comes up. And so even just half of 2 billion is still 1 billion barrels per year. And so about 2.7 million barrels per day. Now, as we walk through this is all hypothetical, that the technology can be and will be in place at some point. Right now, I don't think we could handle that much water in one daily, right? Maybe 2.7 million barrels over a period of time, but not on a daily basis. And so as we think through this, these are hypotheticals, but at least it will give an idea of like the scale of what we're thinking about. Okay, so one of the first ones from an agricultural standpoint, and this is going to be tipped very much into the agricultural sector, is the compatibility or the use of this water for irrigation. So in New Mexico, or in that survey, you noticed it was non-edible crops, and they were specifically focusing on cotton. Okay, we'll talk about some of the social stuff later, but in North Dakota, we do have quite a few ethanol plants. We do have quite a bit of corn, right? And so a lot of that is non-edible, so in a sense. But can we use this water for irrigation, and how much can we actually use? And so as we start going through some of these calculations, we're going to do some assumptions. We're going to assume that we can recycle it to irrigation acceptable limits. Okay, that depends with those limits, but they're a lot lower than what the produced water is right now. We're talking almost clean sort of water. So we have about 2.7 million barrels per day that is usable for irrigation. Okay, and we're going to assume this is, we'll hope that the corn growers and whoever else, but we lengthen it out to 120 days for the growing season. Most of the corn, even in southern Minnesota, it's 98-day corn to 107-day corn, and that's the maturity length that it takes. So that's in southern Minnesota, but we're going to make the assumption that it's 120 days here. And so, okay, how much water can crops use? Well, corn uses about 25 inches per year. That means it wants to utilize that much water per year. Spring wheats, quite a bit less. That's why we grow a lot of spring wheat in this side of the state, is because it can handle more droughty type environments. And then of course, alfalfa is a very high water need crop, but it is also irrigated in many places. So that could make it fairly attractive. So I put the barrels there just so it's sort of contextually, you can kind of think of it from that standpoint. And so corn using about 16,000 barrels per water per year. Okay. So, but we know we get rainfall. We got snow yesterday. So what we're really talking about is supplemental irrigation, not complete 100% irrigation of produced water on the landscape, or 100% irrigation for crops. So on the left is my buddy, Jim Oster. He's from Hazen, and he's probably one of the best salinity, sodicity, irrigation scientists that I know. I've had the pleasure of working with him a little bit, and we did a project down by Hazen. His brother Ernie did supplemental irrigation, and they were worried about salinity and so forth. And so I just wanted to throw a nod to Jim there. But so we're going to assume that we're going to do these back of the envelope calculations. You know, it's kind of magic, and then trust. But so without rainfall over 120 days, you can irrigate about 20,000 acres of corn with that 2.7 million barrels per day. Okay. 20,000 acres is a fair bit, right? And so we're going to talk a little bit about that too. But it was supplemental irrigation. It gets about 55,000 acres. Okay. How many acres are in a section? 640, right? So you can do the math. It's quite a few sections, right? One of the things is obviously our systems aren't set up currently right for irrigation. So we did a project in Rwanda, and the nonprofit had developed 26 pivots on a landscape specifically for irrigation. And so they moved families into communities, and now they can turn the rain on whenever they want. And so, not saying that's going to happen here, but that is something that I've seen, not here, of course. But there are some possibilities. It's just the infrastructure obviously is something that's a little bit challenging. And so, well, that's all fine and dandy for 120 days. But what are you going to do with the other 245 days? Right? And so now you're thinking like, and corn growth isn't linear. Okay, the corn's here, I'm going to use this much water. The corn's up here, I'm going to use this much water. The cycle of the growth of corn in all plants is not linear. And so, but the accumulation can be linear. It's just that the growth pattern is not. And so the other thing as a soil scientist we have to think about is like, okay, we don't see a lot of irrigation out here other than maybe the football fields and soccer fields and things like that. Well, why is that? Well, not all soils are compatible with irrigation. And so here's a map of centered around the Epping area. Everything in yellow is somewhat limited. That could be a soil texture thing. That could be a landscape position or so forth. But there's a lot of red, right? And so that's not even like, don't even try it because it ain't going to work. And so that's one of the things you have to think about with irrigation. It's not like you have, okay, we're going to set a pivot up and we're going to start growing corn around this landscape. It's a lot more complicated with the soils, the infiltration rates, what types of clays, which Robert's going to talk about next. And so, or if you want to go to Arnegard, it doesn't look that much better, right? And this landscape would be very difficult to irrigate. And so in New Mexico and Texas, they're talking about irrigating rangeland to bring back some of the native plants and the establishment of what that looked like pre-settlement. Okay, and so there are opportunities. It's just a bit on the challenging side. So what about for reclamation? Okay, here's a good example of an area that has a bit of a salt to it. You can see the whiteness on the surface there. So how can we use recycled water for reclamation? All right, this is a reclamation conference. So how are we going to do that? So if we said we're just going to take and make the top 3 feet over an acre suitable for crop or plant production. Okay, we're just going to focus on that top 3 feet. One thing we might want to do is flush those salts out, right? We're going to flush the salts. We're going to collect them into a tile drain. We're going to bring them to a disposal facility. After a few, X amount of time, it'll be ready for growth. And so we're going to assume we have 1 acre. We're going to assume we have a soil depth of 3 feet that we want to improve. We're going to assume, this is a big assumption, that the porosity of that soil is 50%. So if you look at what soil is made of, it's about 45% mineral, 50% pores, and 5% organic matter. Okay, and that's what we would think about as a typical soil. And so the pores are either filled with air or water. And so we're going to make the assumption that we're going to fill all those pores with water, because when we do that, then we can start moving water down. Okay, gravitational forces move water down. capillary forces move water in all directions. So as long as we have a head of water up here, water will move down. And so we're going to use this produced water, recycled produced water, as our rinse. Kind of a school of thought is if you triple rinse something, like if you have your pesticide jugs and you triple rinse it, it's considered clean or at least safe for handling. We're going to make that assumption with the soil profile. So we're going to triple rinse the soil. So for that to happen, we have to have 3 rinses at 1.5 feet of water because the soil is 50% pores. So if you have a 3-foot soil, you have to add 1.5 feet of water to get 1 pore volume through that. Okay, so we're going to assume that to be the case. And a lot of this stuff is just engineering, right? And the rest is just sort of back of the envelope calculations, but it's all holds in theory. And so to do that for 1 acre, we would need about 35,000 barrels to triple rinse 1 acre of soil to remove the salt. Okay, that doesn't sound as bad, right? That doesn't sound like 2.7 million barrels per day. So this could almost be something that could be put on site if in fact fresh water was not available. If fresh water is available, obviously that would go down that road. It might be a lot easier. But if in fact it isn't, then you could have a smaller recycling facility in the areas where you need remediation or reclamation, use that water to then work on the reclamation side. Okay, that's a little more palatable than trying to think about 2.7 million barrels per day processing and reusing. So I like this idea and it's doable. And so in a lot of these recycling units, facilities are built for smaller, not for necessarily 2.7 million barrels. And so I think we can do this. Okay, so the other thing is, or one of these other things is this, what I am calling a non-rainy day fund, right? This is when the rain stops and we need to start having water in our aquifers. So this is basically called managed aquifer recharge. So basically what you're going to do is you're going to move water down into the aquifer and store it. So it's not unlike the pore space storage that we're using for other purposes, but we're actually going to move water down into that. And these practices are not uncommon, okay? They're not uncommon. And so even in North Dakota, so this came out last week. I got fortunate that it came out. And so North Dakota is going to look at 3 different aquifers on the east side of the state for managed aquifer recharge. So this is an example of like, okay, if we've depleted our aquifers for other purposes, can we use produced water to then fill those back up again? Okay, and then use it when it's not rain, when the rain stops.
In the grazing systems, and I think most of you probably know this from this side of the state, is water is our most limiting factor for livestock production on rangelands, especially. In North Dakota, a lot of our ranchers still rely on surface waters for watering livestock. And some of that is just that because of locations, it's difficult to get pipelines. As you all know, it's difficult to get a rural water tap or a well dug in this part of the state right now. There's a long delay to get that type of infrastructure in. And what happens though, we have drought frequently as well. And so these are pictures on the right here is the same water system or same pond at different times. It's about a year apart. And so this one's empty, no water is available. What happens if we don't have another water source? We can't graze that pasture. We're hauling water and spending water and hauling water in for those livestock. The other thing that happens is the salts in these waters, and we have a lot of high salts because of our geology in the states. We have high total dissolved solids. We have high sulfates in a lot of our water sources that we use for livestock that can potentially be toxic. And as our water draws down, those salts become more concentrated, and we have lots of loss of livestock during a drought situation. So 21, a lot of livestock died in certain parts of the state because of high sulfates. And so is there a way that we can supplement these waters, whether it's hauling water in? I don't know what that looks like in infrastructure again, right? Do we have pipelines? I don't know what that looks like. But water is definitely the most limiting factor in grazing systems in the state. And this publication talks more about water requirements for different types of livestock. So if you're interested in that, let me know and we can get that to you. The other thing that I have lots of questions maybe, and we need more information. So those that are smarter than us and doing research on what's exactly in these produced waters. So we can't use these for or for human consumption right now. We're not recommended in other states. So what does that look like in terms of residual, if we're consuming meat or products from these animals? Is there carryover of some of constituents? What constituents do we need to be worried about? Is there potential toxicity to these animals with those constituents? We just need a little more information and research on what's in these waters. And I know there's people doing that work. And so this is a list from this publication linked down here of just the different constituents. Right now, what I currently look at in water that's natural in our aquifers, surface waters here in North Dakota, is total dissolved solids. So those total salts, minerals in that water. Sulfates again. So for sulfates, there's different thresholds depending on our animals, but calves, we have to be lower than 500 parts per million. For mature cows, it says 1,000. It really depends on diet. So if they're eating a concentrate diet, so lots of corn, grain, it's that 1,000. If we're on a forage-based diet grazing system, it's closer to 2,500. And that's based off of research from the National Research Council, that all these numbers come from that. Another issue we have across the state, especially when we get in drought, is blue-green algae or cyanobacteria, which can be toxic to animals as well. And so are there nutrients that are coming into these waters that we need to be concerned about, which I think is just more information. What's in the water so we can make sure that we're using them in the correct way and that we're keeping everyone safe when we're using those waters.
So I think it's really important to remember like the intersection between energy and agriculture. So these are two publications that were produced by our ag econ folks at NDSU. And both of them highlight the economic impact of the respective industries on the state of North Dakota. So currently both of the energy and agriculture, it's about $40 billion each. Okay, that's not trivial. We're sitting in a building that is a beautiful, gorgeous building that has been developed and paid for by farmers and ranchers and oil and gas money, right? And so I think it's always important to remember, like, how do we marry agriculture and energy together and not have them being separate entities? And so that being said, though, the coal industry just by itself is about $5.5 billion economic impact. So we are living in one of the most prosperous energy corridors in the country between Bismarck and Divide County. You think about all the energy that's being produced, whether it's hydro, wind, coal, oil, and gas. Solar is not here yet, but it's probably tapping on the door. And so all of these different industries. And so I think it's always important to remember, the prosperity that we have in the state. And so, of course, when we talk about produced waters, you can't hardly talk about produced waters without some of the salt or the total dissolved solids. And so some of that, through some of the publications, we had an excellent graduate student, Aaron Green, who wrote a really good publication on brine and produced waters, found that, on average, it's about 200, the water itself is about 245 grams per liter. That's about 100 pennies of mass in a liter of water. So this water bottle on the front, that's 1 liter. And think about 100 pennies of salt worth in that bottle. It's not trivial. Bill has a jar on his desk in his office that is a mason jar, canning jar, and the bottom of it, it's that much salt in the bottom. And there's certainly salt in the top because it's in equilibrium. And so something to think about as we move through these calculations. So we're going to assume, for the purposes of irrigation and other reasons, we're going to remove that 245. And we're going to assume we have our 2.7. And so, whoa, right? This is like a lot, right? And so to put it in perspective, it's over 1,000 train cars per day of the salt, just salt alone, right? And so you're thinking about this from like, ooh, that's a lot. Well, it is, right? But it's also a lot of produced water. And so thinking about like the waste streams, the reusability, where do these go? There's trade-offs, right? There's trade-offs and things. And so, but hold on, there's a plan. We have a plan, right? And so we're gonna move forward with the plan. So that's where when I was in Houston a couple weeks ago, I met Kyle Murray. Kyle, you want to raise your hand here? Kyle gave one of the first talks, and he focused on the value of the minerals, the value of the elements that is in the brine itself. And so we're going to just kind of talk about it a little bit. A phrase that is used often is elements of interest. Elements of interest. So we're going to talk about these elements of interest. And so Kyle went through a bunch of mathy calculations and so on and so forth, pricing, like how much these different elements are worth over time. And so one of the things that he was able to come up with is like a price, like how much is these elements worth in a barrel of oil. And so we're just going to pick on iodine right now. But right now in North Dakota, iodine's worth about $1 a barrel. Okay, so it doesn't take long to do the math, right? Doesn't take long to do the math that it's about $2.7 million daily that we're pushing back down through the formations of just iodine by itself. Okay, so that's one of the reasons that we think about it from can we bring stuff out of that? Can we become a mineral independent nation? We know a lot of these rare earths, it's a little more complicated today to get those into the US. And so we have to think about it from the standpoint, yes, it might be expensive, but it might be a way that we can become mineral independent because we have it here in North Dakota. Okay, considerations. Technology to achieve large-scale recycled waters. Technology is being developed every day. And so North Dakota does not need to invest into these industries to develop it. People are developing it. We'll just bring it to North Dakota. Centralized or site-specific. Centralizing recycling might be very difficult, but is that the most efficient way? I don't know. So I think that's a consideration. No question mark. Industry will advance. It always does. If there's a will, there's an A, right? We always had that commercial. And so, but I do think if there's a will, there is a way. And finally, what is the social license for reusing produced water? This is not trivial, right? You have to convince the public that it is a usable product. And we think it is from the standpoint of the things we outlined, but of course, that's always a barrier.